Hello, and welcome to the AI Research Roundup. I'm your host, Alex, and today is May 9th, 2025. We're looking at an ICLR conference paper published a bit over 3 months ago, on January 22nd, 2025, titled Improving Probabilistic Diffusion Models with Optimal Diagonal Covariance Matching. Alright, so this paper addresses how probabilistic diffusion models, these are AIs that generate new data like images by reversing a noise process, often require many steps for sampling. That's generating new data. It introduces Optimal Covariance Matching, or OCM, a new method to learn the diagonal covariance, which is a key statistical setting for the noise removal process, aiming to make generation faster. Okay, so this first table, Table 1, compares different covariance choices on the CIFAR10 image dataset. It uses two main scores, Fréchet Inception Distance, or FID, for image quality, and negative log likelihood, or NLL, for how well the model fits the data. Lower is better for both. The table shows that OCMDDPM, the new method, consistently achieves lower Fréchet inception distance and negative log likelihood scores than standard denoising diffusion probabilistic models across different numbers of time steps. These are the stages in generation, especially with fewer steps, pointing to better quality and faster generation. Building on those CIFAR10 results, Table 2 now gives us a broader look at different ways to estimate this crucial covariance. The methods are ranked by their modeling capability. That's their ability to capture complex data features, increasing as you go down the table. It compares covariance types, like simpler XT-independent isotropic ones, to more adaptive XT-dependent diagonal ones. Crucially, the table also lists the additional network passes, or extra computations, needed. The Optimal Covariance Matching method fits in as an XT-dependent diagonal approach, efficiently learning from the score function, which guides the denoising process, using just one additional pass. Okay, so now these plots in Figure 2 give us a visual comparison of Fréchet inception distance versus negative log likelihood on the CIFAR10 dataset again. Each plot represents a different number of sampling steps, k equals 25, 50, 100, and 200, which are the stages in the generation process. We're looking for points closer to the bottom left, as that means better image quality and model fit. And consistently, the red star, representing the optimal covariance matching method, achieves the best balance between these two scores, especially with fewer sampling steps, reinforcing its efficiency. Alright, so shifting from those image quality metrics, Figure 1 here gives us a more foundational look at different covariance estimation methods. Part A shows the training data and the ground truth density, which is the ideal data pattern the model aims to learn. Then, Parts B and C plot the maximum mean discrepancy, or MMD. That's a score for how similar the generated data is to the real data, lower is better, against the number of sampling steps. These plots compare performance in both denoising diffusion probabilistic models and denoising diffusion implicit models, which are another, often faster, type of diffusion model. The optimal covariance matching lines show a quicker drop to lower maximum mean discrepancy, suggesting it more accurately estimates the covariance with fewer steps. Okay, so after examining how closely generated samples match real ones using maximum mean discrepancy, Table 3 now presents results for negative log likelihood. Remember, this score indicates how well the model has learned the underlying data patterns, and lower is better. We see negative log likelihood values here for datasets like CIFAR10, Celeba, and ImageNet across different numbers of sampling time steps. The models incorporating optimal covariance matching with denoising diffusion probabilistic models generally show superior or competitive negative log likelihood, particularly with fewer time steps, underscoring their efficient and accurate data modeling. Following those negative log likelihood results, Figure 3 now shifts focus to a specific type of model, the diffusion transformer, which uses a powerful architecture called a transformer for image generation. These plots show performance on the ImageNet 256 by 256 dataset. On the left, we have Fréchet inception distance versus different classifier-free guidance coefficients, which control how strongly the model follows guidance. Lower Fréchet inception distance is better. On the right, it's recall, a measure of sample diversity, where higher is better versus those same coefficients. The optimal covariance matching methods, especially with denoising diffusion implicit models, tend to show better Fréchet inception distance and notably higher recall, indicating good quality and more diverse images. So to sum up our discussion, from those diffusion transformer results to the broader picture, optimal covariance matching really shines. It enables a more accurate learning of the diagonal covariance for the denoising process. Think of this covariance as the right amount of controlled variation the model needs to effectively remove noise and build the image. This leads to notably improved sampling efficiency, meaning fewer steps, alongside better image quality, diversity, and likelihood. It's a strong overall improvement. Thanks for tuning in to the AI Research Roundup. I'm Alex.